All right, we did it. We're finally at probability. All right. So this is by far like my favorite thing to teach so far, at least. Um, it's new, it's different, it explains kind of how the world works, uh, and it can kind of teach you to think critically. All right. But before we kind of get into this, make sure if you haven't checked in, check into On Campus. Uh, please do that within the next like 5 to 10 minutes. Um, So let me explain kind of what we're going to do today, and a little bit about what we're going to do in the next week or two. So this lesson is technically one lesson in your textbook. Okay, we're going to make that a little bit longer. We're definitely going to cover it, obviously, the rest of this week, and we'll probably be talking about it all in next week too. Um, but this will probably be it. Okay, so this lesson is like the last lesson will be the last lesson of this class. Okay. Ideally, we have more time and we can go a little bit further, but because of obvious things, we can't really do that. All right. Um, so what I want from everyone, and people still aren't here, so I'm going to say this a couple of times probably throughout this. Uh, After this lecture, we need to be on teams because I want to talk a little bit about what your final is going to look like. Okay. And that's going to be really important because I do want your feedback. I have a pretty good idea of what I want it to look like, and it will still require us meeting, but it will be probably less effort than an actual final and or a project. Okay. So please, after this lecture, be on teams. Okay. So now we actually get to like do probability. Everything that we've done so far in this chapter has been a lead up to getting here. All right. Uh, and what we've done so far is we've explained patterns with numbers. So we've done sequences in series. We've added a bunch of things up together using summation notation and a couple of rules. Right. We've seen arithmetic sequences. We've seen geometric sequences. We have defined what those means. We know how to sum them. Um, we know about like how to find the nth term. We know all of that stuff. And if we don't, we're getting there. Okay. Then we got into combinations and permutations. All right. So combinations are given a certain number of things. You need to choose a couple of those. All right. So say you have 6 people in a room and you need a team of 3. How many different combinations are there? Well, there's 6. Choose 3 different combinations of 3 people. Okay. And then last class we went over, well, actually, last class we went over both combinations and permutations. But permutations are an ordering of things. Okay. So it's not necessarily choosing a couple of things, but it's an ordering of those things. Okay. And those both have equations, which we should know, but you can also do it pretty easily on your calculator. Okay, so those 2 equations are very important, and they're gonna come up a lot in what we do over the next couple of days, and really again, like I said, the rest of this semester. Um, so let's get kind of started on it. All right, up here I have a couple of definitions that we need to know because that's what I'm going to be using to talk about a lot of these things. And if I don't use it to talk about, which sometimes I'm bad about using these specific terms, um, if you ever go into math or ever take math in college or ever take statistics in college, which I highly recommend, um, these will be the words that people are using. Okay, so experiment. Okay, an experiment is any happening where the result is uncertain. Period. Okay, so anything you don't know that's going to happen, it is by definition an experiment. Okay, so flipping a coin, you don't know the exact outcome of any one coin flip. So that is an experiment. Rolling a dice, you don't know what number is going to turn up. So that is an experiment. Okay. Um, darts is an experiment because you don't know exactly where your dart is going to land given the fact that you're throwing it. Okay. An outcome is a possible result of an experiment. Okay. So in the coin flip, heads is one outcome, tails is another outcome. Okay. Rolling a dice, rolling a 4 is an outcome, rolling a 2 is an outcome. On a dart toss, right? Hitting a bullseye is an outcome, is a possible outcome. Okay, and then we have sample space. And a sample space is probably one of the most important things on here and probably the thing we're going to spend the most time talking about. Sample space is the set of all possible outcomes. Okay, so in a coin flip, right, our sample space is heads or tails. There are 2 possible outcomes. On a roll of a dice, there are 6 possible outcomes. There's 1, there's 2, there's 3, there's 4, there's 5, there's 6. Okay. Those 2 examples are called discrete, and you don't need to know this right off the bat. But there's 2 types of probability. There's discrete and there's continuous. Discrete experiments have specific outcomes. It can be as little as 2, but no matter what, it has a definite number, right? So again, 2 outcomes with the heads or tails, 6 outcomes with the roll of a dice. And then there are continuous experiments. Okay, so the throw of a dart is pretty close to a continuous experiment because there's no single set of outcomes. Okay, so there are technically, if you want to split up a dartboard into a bunch of points, there are an infinite number of points where that dart can land. Okay, so we're going to be talking about discrete. Continuous is something that you will talk about. I don't think you might talk about it in stats if you take it next year, but you definitely take it in calc-based stats, which is kind of one of those higher level math courses in college. Okay, and you need to do a bunch of calculus to do all that stuff, which you don't necessarily know yet. So we're stuck with discrete for now. Okay, sample spaces. A lot of times it will come down to combinations and permutations, and or using that fundamental counting principle. So that's why I have those up on the board. Okay, so that is what we're going to be talking about today. And those 3 definitions we definitely need to know. Okay, because that's what I'm going to be using to talk about all this stuff. So let's just kind of get used to these terms just for a second. All right. So for example, flipping a coin, and we kind of already did this. At least I talked about it. We want to find the sample space of flipping 1 coin, flipping 2 coins, and flipping 3 coins. But we're actually going to explicitly state what those outcomes, what all those possible outcomes are. Okay. So if you flip a dice, or sorry, if you flip a coin, the sample space is 2 possible outcomes. It is either heads or tails. Those are your only 2 options. Those are the only 2 possibilities that will happen if you ever toss a coin. Okay. Now on 2 coins being flipped, we need to find the sample space of that, which it starts to get a little bit trickier. All right. So let's split this up into the first coin toss and the second. Okay. On the first coin, again, we can get heads. Or we can get tails. And on the second coin toss, we can also get heads or tails. But each of these 2 outcomes can interact with each other differently. Okay, so we could get heads. We could get heads tails. Or we could get tails heads or tails tails. Okay, so in this example, flipping 2 coins, our sample space is this. There are 4 total possible different outcomes that we can have. And if you want to think of it like this, you can actually make a grid, and this is useful, especially dealing with the smaller stuff. All right, we can have our outcomes of our first coin up top, and the outcomes of our second coin on the side, and then just mix those. It's almost like a like combining genes type thing. Punnett square, right? So in this first one, we get heads heads. We get heads tails. Tails heads. And tails tails. And this method will come in handy when we get to mutually exclusive events later on. That won't be today, but thinking about it in terms of area is a really good idea. Okay, so our next example is a little bit trickier. It's 3 coins being tossed. Okay, so if we expand that area metaphor one more time, instead of finding the area of something, we'd be finding the volume of something. Okay, well, I could draw it, right? So we'd have a 3-dimensional, we'd have a cube. We'd have heads, tails up top, heads, tails on the side, and then coming out maybe toward you, we'd have another heads, tails. And we'd have to fill in each one of those mini cubes. Okay. If we did that, we would have a couple more different outcomes, right? So we would have heads, heads, heads. We could have heads, heads, tails. We could have heads, tails, heads. We could have heads, tails, tails. And then we keep doing that, right? So then we would have tails, heads, heads. Tails, heads, tails. Tails, tails, heads. And tails, tails, tails. Okay, so this entire thing that we just did here, that would be our sample space. There are a total of 8 ways, 8 different outcomes if we toss three coins. Okay, the kind of algorithm I use is actually how they use binary. Just as a side note, where this first row is always going to be constant until it has to change when it's filled up with tails. You don't need to worry about that, but that's how binary kind of works. This is exactly like genetic traits. Except in this case, there are 3 different ways, 3 different genes kind of coming into contact. Wouldn't really work, but Yes, it's kind of like that. Okay. So are there any questions about how I got anything up on your screen up until this point? One thing I do want to highlight are the number of different outcomes for each of these, right? So there are two outcomes for each coin, right? On this first experiment where just one coin is tossed, your sample space is 2. On this second experiment where two coins are tossed, there are a total of 4. And on this third experiment, there are 8. Okay, so if you notice something, it's constantly doubling, which means we're multiplying by 2 over and over and over again, which is a geometric sequence. Okay, so again, all of this stuff kind of comes together in this lesson. And we don't need to like make it an nth term of it, but that would be something that useful that you could do kind of later on. All right. So let's actually kind of talk about probability. So the probability of an event, and this is like the formal definition. I'll kind of talk through this a little bit. If an event E has n of E equally likely outcomes, and its sample space S has n of S equally likely outcomes, the probability of E is given by that equation. Okay, so what this means is that we have some experiment, and our desired event has some number of different ways that it can happen. And its sample space S has a total of almost like the count of your sample space. So if you counted up the total number of different outcomes, you'd get n of S. And provided that those are equally likely, the probability of your desired event is the number of ways that can happen over the number of total ways that the experiment can happen. So it's the number of ways your outcome can happen divided by the number of ways your entire experiment can happen. And we'll do an example of that here in a second. So flipping a coin. Let's say we want the probability of heads. Well, the only way we can get that outcome is to flip a heads, right? So there's only one way that can happen. And our sample space is heads or tails. So there are 2 different ways that the experiment can have an outcome. So it's just 1 over 2. Okay, so that's like the most basic example that you can get. Let's say that 2 coins are tossed. What is the probability that both land heads up? So there are 2 things we need to do. We always need to find the sample space no matter what. And then after we find the sample space, we pick out our desired outcomes from that sample space. Okay, so we already kind of did this. Okay, if we have two coins that are being tossed, we get that grid, right? So our first coin can go heads or tails. Our second coin can go heads or tails, which means we have four different outcomes. Heads, heads. Heads, tails. Tails, heads. And tails, tails. Okay, so our sample space, the number of different possible outcomes is 4, right? So we can start writing this. The probability of both heads, so heads, heads, is going to be equal to something over the number of different outcomes. So in this case, our denominator is 4, because there are 4 different outcomes that can happen. And then we look at our sample space and pick out our desired outcome. Okay, so our desired outcome is where both land heads up. And the only time that happens, or the number of times that happens, is just once. So our probability of both landing heads up would be 1/4. Questions about that example? Okay, then we're going to move into slightly bigger numbers. So what is the probability you draw an ace from a standard deck of cards? So again, the first thing we do is we find the sample space. How many possible outcomes are there when we draw a card from a deck? Well, there are 52 cards. So if you just draw one card, there are 52 different possibilities 52 different outcomes that can happen. So our probability of drawing an ace, again, will be the number of times our outcome will happen over the number of total different outcomes. And right now our sample space is just 52, right? Because there are 52 different cards in a deck. And in a standard deck of cards, there are always going to be 4 of any number or any face card. So there are 4 aces in a deck. So we have 4 possibilities of drawing an ace. So our probability of drawing an ace is 4 divided by 52. Okay, questions about that example? And as we go through this, we'll kind of gradually make this a little bit more complicated. So let's say 2 6-sided dice are tossed. What is the probability that they add up to 7? Okay, so the first thing we need to do is we need to find our sample space. So we need to find how many total different outcomes there can be. Well, if you think of each die, as its own event, we can start to use our fundamental counting principle, which is just multiplying the number of different ways that those two events can happen. Well, on event 1, if we're tossing on a standard dice, we have 6 different possibilities, and on the second one we have another 6 different possibilities. So the total number of different possibilities we have is 36, which is our sample space. So if you roll 2 dice, there are 36 different combinations that those dice can have. And if you wanted to list them, you could. It would be 1 1, 1 2, 1 3, 1 4, 1 5, 1 6, 2 1, 2 2, 2 3, 2 4, 2 5, 2 6, and so on. Right? So you could, if you really wanted to, you could make that grid. Right? Where the top is dice 1. And then you'd be basically just finding the area of that box. Okay? But we had that fundamental counting principle, so we can just skip that. Okay? Then we need to find the number of different times our event can happen. Okay, so we want 2 dice to add up to 7. So then we have to think for a second, how do we add up to 7? Well, on dice 1 and dice 2, right? So if we roll 1 on dice 1, we'd have to roll a 6 on dice 2. If we roll a 2 on dice 1, we'd have to roll a 5 on dice 2. Oops. And so on, right? So 3 and 4. 4 and 3. 5 and 2. And 6 and 1. And then we just count those. So there's 6 different possibilities that can happen. So our probability is the number of different times our event can happen over our sample space, which is just equal to 6 divided by 36. Which, if you simplify that, is 1/6. Questions about how I got any of that? Okay, and again, we're going to push that limit, that difficulty just a little bit more. All right, and I want to start talking about winning the lottery. Okay, so we're going to stick with like the pick 6. So you have to choose. So you have 44 options. Right, you have 44 numbers to choose from. You have to pick 6. And if your 6 numbers match the random generator, then you win the lottery. Okay, so we have to think about this real quick. Again, we have to think about the number of different times our event can happen and our sample space. And then our probability is just the number of times our event can happen over our sample space. So there's only one combination of 6 numbers that wins. So we know that our number of different times our event can happen is just going to be 1. The tricky part, and maybe I've kind of clued you into what we're actually going to be doing, is to find our sample space. All right, so in order to find our sample space, we need to determine how many different combinations of six numbers there are within 44. So given 44 numbers, we have to choose 6 of them and then count how many times that happens. And the easiest way to do that is to do 44, choose 6. And I want to walk you through how to do that on a calculator. Okay, so if you have your TI-84 or TI-83 with you, what you would do is you go to Math, you scroll right to Probability, and then scroll down to NCR. And we type in 44 and 6, hit Enter, and we get our number. And then if you hit Enter, you get 1.4166, etc., e to the negative 7th, which if you convert that to a percent, you would get what I have in that box. Okay, so really low, as you would expect. Okay, so that's what I mean when a lot of sample spaces end up being how many different combinations of a number there are. All right, so I want to pause there real quick. Are there any questions about how I got anything on your screen? Okay, so we have 3 more things to talk about in probability. All right, we have independent and mutually exclusive events, and then we have complements of events. If we had a question like this for homework, would the answer in the box be our answer? It would either be that in the box or what you get on your calculator, either one. I just put it in terms of a percent, so that's what you guys normally see. But 1.4166 e to the negative 7th, that's fine too. Okay, so again, we have 3 more things to talk about: independent events, mutually exclusive events, and then complements of events, right? So I'm going to save that for the next class. What I would like you to do, though, is to, as soon as you pause and exit out this video, I want you to go to Teams and wait for me to start a meeting, because I want to talk a little bit about your final, okay? So we've got like one more class of content, and then we'll talk about, and we'll start our kind of like final progress, okay? So I'm going to leave this open for like a minute for general questions, and then the next like 2 to 3 minutes, I'll have that meeting started, and we'll talk a little bit about our final. All right. So meet me on Teams here in a minute. It doesn't seem like there's any general questions, so I'm going to close this and I will see you on Teams.